Imagine feeling the ground shake, and realizing that this is not just an ordinary tremor. Not a passing scare. It is the Earth's crust itself breaking apart. In just a few minutes, entire cities can disappear, the ocean can rise into gigantic waves, and the planet can release an amount of energy greater than thousands of nuclear bombs combined. Around the Pacific Ocean lies a region known as the Ring of Fire, an immense geological scar where tectonic plates collide, slide, and plunge beneath one another. It is there that the most powerful earthquakes in human history occur, but among all of them, there is one that surpasses any other ever measured. An event so extreme that it literally made the Earth oscillate on its axis. An earthquake so strong that its effects were felt on the other side of the planet. And even decades later, it remains a silent warning of what the Earth is capable of doing. That I end this video, we will reveal which was the largest earthquake ever recorded in the Ring of Fire, how it happened, why it was so powerful, and what it teaches us about the risks that still exist today. We will compare this event with other historical mega-earthquakes and analyze recent signs of seismic activity that show the Ring of Fire is far from being at rest, because while we go on with our lives believing that the ground beneath our feet is solid, the planet continues to accumulate tension, and the question is not whether another great earthquake will happen, the question is when, and whether we will be prepared when it happens again. Welcome. Today, we are going to explore the largest earthquake ever recorded in the Ring of Fire. The Earth appears solid, stable, and unchanging, but this feeling is an illusion. Beneath our feet, the planet is in constant motion. Too slow to be perceived in everyday life, yet powerful enough to destroy entire cities in seconds. Nowhere else in the world does this force manifest itself as intensely as in what is known as the Pacific Ring of Fire. The Ring of Fire is not a specific place, nor a visible line on ordinary maps. It is a vast geological region that surrounds almost the entire Pacific Ocean, forming an unstable arc that crosses continents, oceans, and islands. It is there that the Earth releases most of its accumulated internal energy. Approximately 90% of all earthquakes on the planet occur within this region. The largest earthquakes ever recorded in human history were born there, and this does not happen by chance. The Ring of Fire exists because the Pacific is the stage of the most violent confrontation between the Earth's tectonic plates. The Earth's crust is not a single, continuous layer. It is fragmented into enormous rigid blocks, called tectonic plates, which float over a hotter, partially solid layer of the mantle. These plates are constantly moving, driven by deep forces coming from within the planet. The Pacific Ocean is dominated by the Pacific Plate, the largest tectonic plate in existence. Around it, virtually all of its edges are in direct contact with other plates, and in most cases, this contact is not peaceful. The plates do not drift apart smoothly, they collide. When an oceanic plate collides with another plate, whether continental or oceanic, the denser one is forced to plunge into the Earth's interior. This process is known as subduction, and it is the heart of the Ring of Fire. Subduction creates some of the most extreme geological structures on the planet: deep ocean trenches, chains of explosive volcanoes, and gigantic seismic faults. But above all, it creates zones of stress accumulation. The plates do not slide smoothly over one another. They become stuck, locked by friction. Meanwhile, they continue to be pushed by immense tectonic forces. Energy slowly builds up over decades, centuries, or even millennia, until the rock can no longer withstand it. When this energy is released suddenly, the Earth shakes, and when the rupture area is extensive, the result is a mega-earthquake. This is exactly what makes the Ring of Fire so dangerous. The subduction zones around the Pacific are long, deep, and extremely active. Some of them extend for hundreds, even thousands of kilometers. This allows gigantic ruptures to occur all at once. In addition, the Pacific's oceanic plates are cold and dense. This type of plate tends to deform less before breaking, which means that when rupture occurs, it is more violent, releasing colossal amounts of energy in just a few seconds. Another crucial factor is the ocean itself. Many of the largest earthquakes in the Ring of Fire occur beneath the seafloor. When the ocean floor is abruptly displaced, millions of tons of water are pushed upward, generating tsunamis capable of crossing entire oceans. This transforms local earthquakes into global catastrophes. The Ring of Fire is not just a seismic region. It is a dynamic, interconnected system, where the movement of one plate directly influences the behavior of another. The release of energy at one point can alter the balance of stresses in distant regions, preparing the ground for new earthquakes. That is why major seismic events in the Pacific are rarely seen as isolated phenomena by modern science. They are part of a larger, continuous cycle that has been underway long before human existence, and will continue long after. What is most unsettling is that the Ring of Fire never truly rests. It only alternates between periods of intense activity and apparent silence, and this silence does not mean safety. It simply means that energy is once again being slowly accumulated deep within the earth. That is why the Pacific Ring of Fire concentrates the largest earthquakes on the planet, not because it is exceptional, but because it is the point where the deepest forces of the earth meet, collide, and inevitably rupture. On May 22, 1960, the planet experienced something that had never been recorded before, and that, to this day, has never been surpassed. On that seemingly ordinary Sunday, southern Chile woke up unaware that it was about to enter Earth's history. It was not just another earthquake. It was the largest seismic event ever measured by modern science. A rupture so extreme that it redefined how we understand the energy released by the planet. At 3:11 p.m. local time, the Earth began to shake, and it did not stop. What followed was a magnitude 9.5 earthquake, known today as the Great Valdivia Earthquake. An event so powerful that it shook not only Chile, but the very physical balance of the planet. To understand the scale of this earthquake, it is necessary to abandon any comparison with common tremors. An earthquake of this magnitude is not just stronger. It is exponentially more energetic. Each increase of 1 point on the magnitude scale represents about 32 times more energy released. This means that the Valdivia earthquake released an amount of energy that surpasses any seismic event ever observed before or since. The rupture occurred along an extensive subduction zone where the Nazca Plate dives beneath the South American Plate, a fundamental part of the Pacific Ring of Fire. For decades, possibly centuries, these plates remained locked, silently accumulating tension. When the fault finally gave way, it ruptured across a colossal extent, estimated at more than 1,000 kilometers. It was not a single point that broke, but a continuous sequence of faults releasing energy in a chain reaction. The ground rippled as if it were liquid, rivers changed course, lakes overflowed, entire areas sank while others rose several meters. Cities like Valdivia, which ultimately gave the earthquake its name, were devastated. Buildings collapsed as if they were made of paper. Infrastructure vanished in seconds. Entire communities were cut off from the rest of the country. But what makes the 1960 earthquake even more singular is that it did not end when the ground stopped shaking. The energy released was so immense that the entire planet reacted. Seismographs around the world recorded seismic waves traveling repeatedly around the Earth, as if the planet had been struck with enough force to vibrate for days. These waves circled the globe several times, being detected even in regions completely opposite Chile. For the first time, science had clear evidence of how a mega-earthquake can make the entire Earth ring like a bell. In addition, the event physically altered Chilean territory. Parts of the coast sank permanently, while others were uplifted. Some areas were submerged forever. Others emerged from the ocean, creating new landscapes. The earthquake also exposed a disturbing reality: humanity was not prepared to deal with events of this scale. In 1960, seismic monitoring systems were still limited. The moment magnitude scale used today did not yet fully exist. The Valdivia earthquake helped drive fundamental advances in modern seismology, forcing scientists to rethink how large earthquakes are measured, analyzed, and understood. Until then, it was believed that there was a practical limit to earthquake magnitude. Valdivia shattered that idea. It proved that, under the right conditions, the Earth is capable of releasing energy at levels that defy human imagination. And more than that, it showed that the subduction zones of the Ring of Fire are capable of producing the most extreme events ever witnessed. The psychological impact was also profound. For survivors, it was not just a natural disaster. It was the feeling that the very ground, that which should be stable, had become the enemy. Accounts from the time describe endless minutes of shaking, deep sounds coming from the earth, the near-simultaneous collapse of structures, and a complete loss of spatial orientation. People were unable to remain standing. Others described the sensation of being on invisible waves. The Valdivia earthquake was not an isolated event in geological time. It was the inevitable result of tectonic processes that remain active to this day. The same plate, the same subduction zone, the same relentless logic of Earth's dynamics. That is why this earthquake is not just a historical memory. It is a scientific milestone and a permanent warning. It shows what happens when the Ring of Fire releases centuries of accumulated energy in a single event. It shows that the Earth does not operate on human timescales, but on geological ones, where silence can last for generations, until everything changes in a matter of minutes. The Great Valdivia earthquake remains, to this day, the ultimate benchmark against which all other earthquakes are compared. None has come close to releasing so much energy. None has altered scientific understanding of the planet so profoundly. And perhaps the most disturbing thing of all is this: the Ring of Fire that produced the most powerful earthquake in history remains active. The same forces that acted in 1960 are still in motion, invisible, silent, accumulating tension once again. The Earth does not forget that it only waits. When the ground finally stopped shaking in southern Chile on May 22, 1960, many believed the worst was over. The silence that followed seemed to signal the end of the terror. But in reality, the earthquake had been only the beginning of something even greater, broader, and impossible to contain. The planet had released its energy, now, the oceans would respond. The Valdivia earthquake was not only the largest ever recorded, it was one of the few events capable of triggering a global reaction. The colossal rupture on the ocean floor displaced unimaginable volumes of water. The Pacific, until then seemingly calm, began to reorganize itself violently. What formed there was not a common wave, that it was a megatsunami. Unlike the waves visible at the surface, tsunamis are born almost imperceptibly in the open ocean. They spread silently across the sea, traveling at speeds close to 800 kilometers per hour, carrying enough energy to cross entire liquid continents. In Chile, the consequences were immediate. Shortly after the earthquake, coastal communities began to notice an unsettling phenomenon: the sea was retreating abnormally, exposing the ocean floor. To many, it seemed curious. To others, it was an omen. Minutes later, walls of water advanced over the coast, destroying entire villages. Port cities vanished, vessels were thrown kilometers inland, infrastructure already weakened by the earthquake was simply swept away. But the impact of the 1960 earthquake was not confined to Chile. As seismic waves dissipated through the Earth's crust, ocean waves crossed the Pacific in all directions. The tsunami became a global messenger of tectonic violence. In Hawaii, more than 10,000 kilometers from the epicenter, the ocean began to behave strangely hours later. When the waves arrived, some exceeded 10 meters in height, flooding coastal areas, destroying homes and ports, and causing deaths. In Japan, on the opposite side of the Pacific, the tsunami struck coastal villages with enough force to drag entire structures away. Communities that had not felt the earthquake were suddenly hit by a disaster coming from the ocean, with no local warning, no prior shaking. Even regions such as the Philippines, New Zealand, and parts of the west coast of North America recorded effects from the tsunami. The entire Pacific had become an interconnected system of energy propagation. This event revealed something disturbing. A mega-earthquake in the Ring of Fire does not belong only to the country where it occurs. It becomes a planetary phenomenon. In Chile, the consequences were deep and long-lasting. It is estimated that more than 2 million people were directly affected. Cities were isolated for weeks. Communication systems collapsed. Hospitals improvised care amid the rubble. Beyond the immediate destruction, the earthquake caused permanent changes to the region's geography. Parts of the coastlines sank several meters, allowing the ocean to invade areas that had previously been dry land. Other regions were uplifted, creating new stretches of land. Rivers changed course. Lakes overflowed. A landslide triggered by the earthquake blocked the drainage of Lake Rhinihu, creating an unstable natural dam that threatened to flood entire cities weeks after the main shock. The danger persisted even when the ground was no longer shaking. The human response to the disaster was marked by improvisation. In 1960, tsunami warning systems were virtually non-existent on a global scale. Many countries struck by the tsunami received no warning at all. The ocean simply arrived. This event was a turning point for science and for natural risk management. For the first time, it became clear that oceanic earthquakes require coordinated international responses. From the lessons of 1960, the first efforts to create global tsunami monitoring systems in the Pacific began to emerge. The earthquake also changed the way scientists understand the transfer of energy between the Earth's crust and the oceans. It demonstrated that the interaction between tectonics and hydrodynamics can amplify catastrophes exponentially. But perhaps the deepest impact was psychological. The Valdivia earthquake shattered the idea that natural disasters have predictable limits. It showed that the Earth is capable of exceeding any human expectation when the right conditions align. It showed that the ocean, which sustains life, can also transform into a vector of silent destruction. Even decades later, the 1960 event continues to be studied as an extreme model. It serves as a reference for modern tsunami simulations, coastal urban planning, and seismic risk assessment in subduction zones. And there is a disturbing detail that cannot be ignored: the 1960 earthquake was not an isolated event within the context of the Ring of Fire. It is part of a sequence of mega-earthquakes that have occurred, and continue to occur, along the edges of the Pacific. Each one carries the possibility of repeating, on a greater or smaller scale, the same devastating effects. The 1960 megatsunami showed that the true reach of a great earthquake is not limited to solid ground. It extends across the oceans, connects continents, and transforms a local geological event into a global crisis. The Ring of Fire, in this sense, is not just a region of earthquakes. It is a system capable of influencing the entire planet in a matter of hours. And when the Earth decides to move in this way, there are no borders, distances, or oceans capable of containing its consequences. On the night of March 27, 1964, while much of the world went about its routine without any suspicion, the far north of the planet became the stage for one of the most violent geological events ever recorded by humanity. Alaska, a vast, cold, and seemingly untouched region, became the epicenter of an earthquake so powerful that it still ranks second among the largest in modern history. At 5:36 p.m. local time, the earth began to move, and it was not a common tremor. The ground started to vibrate with increasing intensity, as if something gigantic were tearing apart deep within the planet. The earthquake lasted about 4.5 minutes, a duration that, in seismic terms, is almost interminable. For those who experienced it, it felt as if the planet had lost any sense of stability. With a magnitude of 9.2, the 1964 Alaska earthquake, also known as the Great Friday Earthquake, was a brutal reminder that the Pacific Ring of Fire is not dangerous only in tropical or densely populated regions. Even remote areas can release colossal amounts of energy accumulated over centuries. The origin of the earthquake lies, once again, at the heart of the Ring of Fire, an active subduction zone where the Pacific Plate dives beneath the North American Plate. This region, known as the Aleutian Subduction Zone, stretches for thousands of kilometers along the arc of the Aleutian Islands. For decades, this tectonic boundary had remained relatively quiet. But silence, as science now knows, is not a sign of safety, it is a sign of accumulating tension. When the fault finally gave way, the rupture spread across an estimated length of about 800 kilometers. The Earth's crust shifted abruptly, with some areas being uplifted by several meters, while others subsided almost instantaneously. Cities such as Anchorage, Alaska's largest city, suffered severe damage. The ground literally behaved like a fluid. Entire neighborhoods slid toward the sea. Roads cracked apart. Bridges collapsed. Railway lines twisted as if they were made of malleable metal. But the earthquake was not limited to the destruction caused by the shaking itself. As in 1960, the displacement of the ocean floor generated a series of devastating tsunamis. However, the Alaska event revealed an even greater complexity. In addition to the main tsunami generated by the tectonic rupture, multiple local tsunamis occurred, triggered by submarine and coastal landslides. These local tsunamis were particularly deadly because they struck coastal areas almost immediately, leaving no time for any human reaction. In some locations, waves exceeding 60 meters in height were recorded in narrow fjords, further amplifying the destructive power of the water. The impact was not confined to Alaska. Tsunami waves traveled across the Pacific, reaching the west coast of Canada, the United States, and even distant regions such as Hawaii. Once again, it became evident that mega-earthquakes in the Ring of Fire have transoceanic reach. The 1964 earthquake also played a fundamental role in advancing seismic science. Unlike in 1960, scientific instrumentation was already more developed. Networks of seismographs recorded the event with greater precision, allowing researchers to analyze, in unprecedented detail, the propagation of seismic waves and the behavior of the crust during a mega-earthquake. It was from this event that the theory of plate tectonics, still relatively recent at the time, gained definitive confirmation. The Alaska earthquake provided clear evidence that plates move as rigid units, interacting at well-defined boundaries and releasing energy episodically. In addition, the event revealed something crucial: the duration of an earthquake is just as important as its magnitude. The long shaking time contributed significantly to structural collapse, the triggering of landslides, and prolonged ground instability. The human impact, although smaller in absolute numbers of victims compared to other disasters, was profound. Entire communities were displaced. Vital infrastructure had to be rebuilt from scratch. The economic cost was immense, especially considering the complex logistics of such an isolated region. But perhaps the greatest contribution of the Alaska earthquake was strategic. It led to a complete revision of building codes in seismic regions. Engineers began to consider not only the strength of shaking, but also its duration, soil liquefaction, and secondary effects such as tsunamis and landslides. The event also reinforced the need for continuous monitoring of subduction zones, even in areas that appear stable. The idea that large earthquakes are rare and unpredictable events began to give way to a more realistic understanding. They are inevitable in certain tectonic contexts, the question is only when. The 1964 earthquake showed that the ring of fire does not follow a single pattern. It can release its energy in densely populated regions or in remote areas. It can generate global tsunamis or extremely destructive local ones. It can last seconds or interminable minutes. Above all, it is unpredictable in form, but inevitable in essence. Like the Valdivia earthquake, the Alaska event remains a permanent reminder of the scale of the forces operating beneath our feet. It shows that the planet does not distinguish political borders, population density, or technological level. When tension accumulated over centuries finally breaks, the Earth simply does what it has always done, and it will continue to do so. On the morning of December 26, 2004, while millions of people around the Indian Ocean were celebrating the holiday season and year-end festivities, the Earth ruptured in a way that would forever change humanity's perception of the power of earthquakes and tsunamis. At 7:58 a.m. local time, a deep tremor began near the northern coast of the island of Sumatra, Indonesia. Within seconds, it became clear that this was not an ordinary earthquake. The ground did not merely shake, it seemed to slide, ripple, and violently reorganize itself. What was happening there was the rupture of one of the largest subduction zones on the planet, an essential part of the tectonic system that makes up the Ring of Fire and its extensions across the Indo-Pacific. The Indo-Australian plate was plunging beneath the Eurasian plate, accumulating tension for centuries. At that moment, that tension was released all at once. The earthquake reached a magnitude of 9.1, placing it among the most powerful ever recorded by humanity. The rupture propagated along an astonishing length of about 1,300 kilometers across the ocean floor, a colossal fracture comparable to the length of several countries lined up end to end. The vertical displacement of the seafloor was brutal. In some areas, the ocean bed rose several meters in just a few seconds. This sudden movement pushed enormous masses of water upward, triggering a chain reaction impossible to contain. One of the most devastating tsunamis in modern history was born. Unlike many other major earthquakes, the 2004 event occurred in a densely populated region, with tens of millions of people living close to the coast. And at that time, there was no tsunami warning system in the Indian Ocean. The ocean moved in silence. On several beaches, the sea receded dramatically minutes after the tremor. The ocean floor was exposed, revealing fish, coral, and stranded boats. To many, it seemed like a curious phenomenon. To others, it was a sign no one had been taught to recognize. Minutes later, walls of water advanced onto the coast. In Indonesia, especially in the province of Aceh, entire villages vanished. Houses, roads, mosques, and schools were ripped from the ground and dragged inland. The destruction was so complete that, in some areas, no recognizable geographic references remained. But the tsunami did not stop there. The waves crossed the Indian Ocean at impressive speed, striking Sri Lanka, India, Thailand, Malaysia, the Maldives, and even regions along the east coast of Africa. In each place, the impact was different, but equally devastating. In some locations, waves arrived with heights exceeding 30 meters. In others, the force of the water was enough to penetrate kilometers inland. Within a few hours, the disaster had become a truly global tragedy. The death toll was staggering. It is estimated that more than 230,000 people lost their lives as a direct consequence of the earthquake and tsunami. Millions were left homeless. Entire communities were wiped off the map. But beyond the human dimension, the 2004 earthquake caused measurable physical effects on the planet itself. The release of energy was so intense that Earth's rotation underwent a subtle yet detectable change. The planet's axis shifted by a few centimeters, and the length of the day was shortened by fractions of microseconds. It was further proof that mega-earthquakes are not merely regional events, they affect the planetary system as a whole. The event also made it clear that the Ring of Fire and its associated zones are dangerous not only because of earthquake magnitude, but because of the lethal combination of released energy, oceanic environment, and human vulnerability. Unlike regions such as Chile or Japan, where populations had lived with seismic threats for generations, many of the areas affected in 2004 had no recent historical memory of tsunamis of that scale. The absence of a risk culture turned a natural phenomenon into an amplified catastrophe. The international response to the disaster was immediate, but it exposed deep flaws in global preparedness for such events. After 2004, tsunami monitoring and warning systems began to be implemented in the Indian Ocean, inspired by models already in place in the Pacific. The Sumatra, Andaman earthquake became a case study of extremes. It helped science better understand how extraordinarily long ruptures behave, how tsunamis propagate through complex ocean basins, and how small vertical displacements of the seafloor can generate waves of continental-scale destruction. But perhaps the harshest lesson was this: the Earth does not give warnings according to the human calendar. The 2004 earthquake occurred at a moment of apparent tranquility, on a day associated with celebration, rest, and tourism. It showed that the Ring of Fire and its tectonic extensions do not follow moral, social, or cultural patterns. They follow only the physical laws of geology. Like Valdivia in 1960 and Alaska in 1964, the Sumatra, Andaman event reinforced an uncomfortable truth: the largest earthquakes on the planet are not improbable exceptions, they are inevitable consequences of an active tectonic system. The Pacific, the Indian Ocean, and their margins continue to accumulate tension. And when that tension breaks, the impact goes far beyond any border. The 2004 earthquake was not just a historical tragedy, it was a global reminder that we live on a planet in constant motion, and that, in the face of it, humanity is still fragile. On the afternoon of March 11, 2011, Japan, one of the most prepared nations in the world for natural disasters, was confronted with a reality that not even its advanced technology could contain. At 2:46 p.m. local time, the ground began to shake in the northeastern region of the country, near the coast of the island of Honshu. Within seconds, seismic sensors triggered automatic alerts, bullet trains braked, and industrial systems entered emergency mode. Everything worked as planned. But what was about to happen went far beyond any scenario that had been anticipated. The Tohoku earthquake reached a magnitude of 9.1, becoming the most powerful ever recorded in Japan's history and one of the strongest on the planet. The rupture occurred along the Japan subduction zone, where the Pacific Plate dives beneath the Okhotsk Plate, part of the tectonic system of the Pacific Ring of Fire. For decades, this region had been silently accumulating tension. The oceanic plate, cold and dense, advanced just a few centimeters per year, becoming locked beneath the upper plate. Pressure increased, invisible, constant, inevitable. When the fault finally gave way, the displacement was extreme. In some areas, the seafloor moved more than 50 meters horizontally and several meters vertically. It was one of the largest displacements ever measured in a single seismic event. The Earth's crust ruptured along hundreds of kilometers, releasing a colossal amount of energy in just a few minutes. The shaking was felt across virtually the entire Japanese archipelago. Buildings swayed for long minutes. People struggled to remain standing. Even structures designed to withstand major earthquakes suffered significant damage. But, as with other mega-earthquakes of the Ring of Fire, the greatest danger was still to come. Just minutes after the main tremor ended, the ocean began to recede alarmingly along the northeastern coast of Japan. Tsunami sirens sounded. Alerts were broadcast on radio, television, and mobile phones. Millions of people tried to move to higher ground. The tsunami that formed was not a single wave, but a sequence of walls of water that advanced with devastating force. In some regions, waves exceeded 40 meters in height, overtopping dikes, seawalls, and barriers designed based on previous historical events. Entire coastal cities were swallowed. Within minutes, neighborhoods disappeared beneath the water. Ships were hurled inland. Vehicles, houses, factories, and critical infrastructure were swept away as if they were weightless. The tsunami advanced kilometers inland, turning urban areas into fields of debris. The human impact was immense. More than 18,000 people lost their lives or went missing. Hundreds of thousands were left homeless. Entire communities had to be permanently evacuated. But the Tohoku earthquake revealed something even more disturbing: not even maximum preparedness guarantees absolute safety. Japan had one of the most advanced tsunami warning systems in the world. Strict building codes. A deeply rooted culture of prevention. Even so, the magnitude of the event exceeded what had been considered plausible. The tsunami also struck the Fukushima Daiichi nuclear power plant, causing a cascading failure in the cooling systems. The result was the most serious nuclear accident since Chernobyl. Once again, a geological event triggered technological consequences of global reach. The 2011 earthquake forced a profound reassessment of risk management strategies in Japan and around the world. Scientists realize that models based solely on historical records are insufficient to predict extreme events in subduction zones. Tohoku showed that faults considered locked can release energy accumulated over millennia, not just decades. It showed that the upper limit of seismic magnitude in certain regions had been underestimated. The event also provided unprecedented scientific data. GPS networks recorded the displacement of large portions of Japanese territory in real time. Parts of the island of Honshu moved more than 2 meters eastward. The Earth's axis underwent a small but measurable shift. The entire planet responded to the earthquake. But perhaps the most profound lesson of Tohoku was symbolic. It showed that the Ring of Fire does not distinguish between rich or poor countries, advanced or vulnerable ones. When accumulated energy is released, the scale of the phenomenon surpasses any human system of control. The Tohoku earthquake was not just a natural disaster. It was a shock of reality. A reminder that, despite all accumulated knowledge, the Earth still operates on scales that challenge our capacity for prediction and response. Like Valdivia, Alaska, and Sumatra, Tohoku occupies a definitive place in the history of the great earthquakes of the Ring of Fire. It marks the moment when humanity realized that the limits of what is possible have not yet been fully mapped. And as the Pacific continues to move, silently, that realization remains. The Earth did not stop that it simply released another part of its power. In late July 2025, the Pacific Ocean once again demonstrated just how powerful and unpredictable it can be, reminding the world that the forces accumulating beneath tectonic plates recognize neither borders nor human timelines. On the morning of July 30, 2025, a massive earthquake struck the eastern coast of Russia's Kamchatka Peninsula, one of the most dynamic and geologically active regions of the Pacific Ring of Fire. At 11:24 a.m. local time, a deep tremor began in the ocean, about 119 kilometers east-southeast of the city of Petropavlovsk-Kamchatsky, shaking the ground for approximately 4.5 minutes, an eternity when we are talking about tectonic energy released all at once. With an estimated magnitude of 8.8, this earthquake was classified as one of the largest ever recorded in the world in decades, comparable to the most extreme events of the modern instrumental record, and the largest to strike the region since 1952. This large-scale rupture occurred in the area known as the Kamchatka Trench, where the Pacific Plate slides beneath the North American Plate, a tectonic boundary characteristic of subduction zones that accumulate tension over long periods before releasing it abruptly and violently. The earthquake was strongly felt across the entire peninsula and also in several coastal areas across the Pacific. Although the most densely populated regions were relatively spared from direct destruction, the intensity of the shaking was sufficient to cause damage to local infrastructure, such as cracks in building facades, power supply interruptions, and partial collapses, effects that led authorities to declare a state of emergency in cities like Petropavlovsk-Kamchatsky. Immediately, the tremor triggered tsunami alerts and warnings across vast portions of the Pacific Ocean, including Japan, Hawaii, North America, and countries in South America. In many cases, these warnings were revised or gradually cancelled in the days that followed, thanks to rapid analysis of oceanographic data and the accumulated experience of warning systems since previous disasters such as those of 2004 and 2011. Along the Kamchatka coast itself, waves generated by the displacement of the seafloor reached significant heights, with records of 3 to 4 meters in some areas, flooding ports and industrial zones and dislodging boats from their moorings. In localities such as Severokurilsk, reports and images of waves inundating urban and port areas circulated widely in the media and on social networks, illustrating the force with which the tsunami interacted with the local coastal environment. On more distant islands and in regions of the North Pacific, the waves were smaller but still noticeable. In Hawaii, for example, records indicated oscillations of up to 1.7 meters, while in Japan waves of about 0.6 meter reached coastal areas, enough to cause concern among authorities and residents, who in many cases responded quickly with preventive evacuations. The magnitude 8.8 earthquake occupies a prominent place among the largest seismic events in the world documented by modern instruments, often cited as the largest since the 2011 Tohoku earthquake and comparable to other major events in the record, such as the 1906 Ecuador, Colombia and the 2010 Chile earthquakes, ranking as the sixth most powerful ever measured. One of the immediate consequences of this event was the emergence of an extensive sequence of aftershocks, something common after mega-earthquakes. Specialists from the United States Geological Survey, USGS, and other international institutions warned that in the weeks and months that followed, numerous additional tremors were likely to be recorded, many of them strong enough to be felt by the local population and to pose additional risks to already weakened structures. Another important aspect of the 2025 event was the coordinated response among different countries. Although the earthquake occurred in a geographically remote region, the tsunami warning systems activated in nations such as Japan, the United States, Russia, and countries along the west coast of the Americas reflected a level of technical cooperation developed over decades of learning from previous disasters in the Pacific. Despite the extraordinary magnitude of the tremor, there have so far been no widespread reports of catastrophic damage in densely populated areas or of major loss of life, a reflection of both the remote location of the epicenter and the relative effectiveness of the emergency response systems that were rapidly activated in coastal zones threatened by the tsunami. The 2025 Kamchatka mega-earthquake is therefore a contemporary example of how the tectonic forces of the Ring of Fire remain capable of generating extreme events even in the 21st century, directly linking millennia-old geological principles to tangible impacts in the present. It shows that major tectonic ruptures continue to be a latent reality along the edges of the Earth's plates, and that vigilance, science, and global warning systems are indispensable tools for mitigating risks and protecting populations in the face of these powerful natural phenomena. The 2025 Kamchatka earthquake drew worldwide attention not only because of its extreme magnitude. It became a global event because, within a few dozen minutes, it activated virtually the entire Pacific Ocean tsunami alert architecture, revealing how a single tectonic rupture is capable of placing dozens of countries on simultaneous high alert. This domino effect does not happen by chance. It is a direct consequence of Kamchatka's strategic geological position within the Ring of Fire and of the specific type of earthquake that occurred there. Unlike many strong earthquakes that happen within continental interiors or along transform faults, the Kamchatka earthquake was a subduction megathrust earthquake, the most dangerous type on the planet when it comes to tsunamis. These earthquakes do not merely shake the ground, they move the ocean floor, displacing billions of tons of water almost instantaneously. It is this vertical displacement of the seafloor that turns an earthquake into a transoceanic threat. In the Kamchatka region, the Pacific plate has been plunging beneath another plate at a constant rate for millions of years. This movement is not smooth. The plates become locked, jammed by friction, silently accumulating energy. When rupture finally occurs, it does not happen at a single point, but along hundreds of kilometers of fault. In the case of the 2025 event, the data indicated an extensive, deep rupture that was extremely efficient at transferring energy to the column of water above it. It was precisely this scenario that triggered tsunami warning centers almost immediately after the tremor. Seismic sensors detected the high magnitude within minutes. Soon after, ocean buoys and tide gauges began recording abnormal changes in sea level. Even before the final wave heights were confirmed, international protocols dictate that, when an earthquake of this size occurs in an oceanic subduction zone, alerts must be issued without hesitation. The psychological impact of this process is enormous. In countries such as Japan, the United States, Chile, Mexico, and several Pacific Island nations, sirens sounded, emergency messages were sent to mobile phones, and coastal populations were instructed to evacuate low-lying areas. In many places, the tsunami ultimately turned out to be small or moderate. But the logic of prevention is not based on certainty, it is based on the worst possible scenario. The Kamchatka earthquake also drew global attention because it occurred in a region that geologists classify as capable of producing even larger events. The Kuril-Kamchatka Trench has been responsible in the past for some of the largest earthquakes of the 20th century. This means that any extreme event there is immediately analyzed not only as an isolated episode, but as part of a larger tectonic cycle. The question echoing among scientists was not just, what happened, but what does this mean for the future of the region? Another decisive factor was the prolonged duration of the shaking. Truly large earthquakes are not brief explosions. They can last several minutes, with the ground moving in a continuous, almost undulating manner. This type of motion drastically increases the likelihood of seafloor displacement and raises the risk of submarine landslides, which can also generate secondary tsunamis. Even when the initial waves are not gigantic, these collapses can amplify local effects. In addition, the event occurred at a historical moment when the world is more attentive to extreme natural risks. After the disasters in the Indian Ocean in 2004 and in Japan in 2011, massive investments were made in monitoring and communication systems. The Kamchatka earthquake effectively served as a real-time test of this global network. The fact that alerts were issued within minutes demonstrated important advances, but also exposed how dependent humanity has become on systems that must function perfectly under enormous pressure. Global attention was also fueled by initial uncertainty. In the first hours after the tremor, tsunami models presented varied scenarios, some indicating potentially dangerous waves in regions very far from the epicenter. This happens because tsunami propagation is not uniform. It depends on ocean depth, submarine topography, and the shape of the coastlines the waves encounter. The same event can be almost imperceptible in one country and devastating in another. Kamchatka, despite being remote, is connected to the entire Pacific by these invisible highways of oceanic energy. The earthquake made it clear that no Pacific coastal region is completely isolated when a megathrust earthquake occurs in the Ring of Fire. Even relatively small waves can generate dangerous currents, damage ports, drag vessels, and put lives at risk. Finally, the event gained worldwide prominence because it reinforced an uncomfortable truth: the Earth remains active, dynamic, and unpredictable, regardless of human technological advancement. The Kamchatka earthquake was not just a one-day news story. It became a reminder that we live atop constantly moving plates and that the greatest natural risks on the planet do not belong to the past, they continue to form, right now, beneath the oceans. This episode showed that the Ring of Fire is not merely a geographic or scientific concept. It is a living system, in permanent tension, capable of impacting the entire planet within hours. And that is precisely why events like Kamchatka are not treated as local problems, but as global matters, monitored in real time by scientists, governments, and millions of people around the world. When a major earthquake occurs, the first question that echoes around the world is almost always the same: what was the magnitude? That number becomes a headline, a historical reference, and often the main parameter used to judge the danger of a seismic event. But behind this seemingly simple value lies a long, complex, and deeply scientific story about how humanity gradually learned to quantify the invisible force accumulating beneath our feet. For most of human history, earthquakes were described only by their effects. Destroyed cities, collapsed churches, fires, tsunamis, and accounts of collective panic were the only ways to record the severity of a tremor. There were no universal numbers, no instruments capable of translating the Earth's motion into comparable data. Each earthquake was an isolated event, impossible to reliably compare with another that occurred in a different place or time. It was only in the 20th century that science took a decisive step towards standardization. With the development of the first modern seismographs, it became possible to record seismic waves with precision. For the first time, the Earth wrote its movements on paper, allowing scientists to analyze not just visible damage, but the actual energy released within the planet. The first major attempt to turn earthquakes into comparable numbers came with the famous Richter scale. Created in the 1930s, it was revolutionary for its time. For the first time, a single numerical value allowed earthquakes to be compared based on the amplitude of seismic waves recorded by a standard instrument. What few people realize, however, is that the Richter scale was never designed to measure megathrust earthquakes like those of the Ring of Fire. As increasingly large earthquakes were recorded, the limitations of that scale became clear. Giant tremors, especially those occurring in subduction zones, simply saturated the method. Two earthquakes with vastly different energies could end up with similar values, masking enormous differences in real power. This created a serious problem: how could the largest earthquakes in history be compared accurately? The answer came with the development of the moment magnitude scale, now the international standard for measuring large earthquakes. Unlike older scales, it is not based solely on wave size, but on fundamental physical parameters of the earthquake: the area of the fault that ruptured, how much the plates slipped, and the rigidity of the rocks involved. In other words, it measures the actual energy released by the planet. This shift was crucial for understanding why some earthquakes enter history as truly exceptional events. A seemingly small increase in magnitude does not represent a linear difference, but an exponential one. Each whole number increase corresponds to about 32 times more energy released. This means that a magnitude 9 earthquake is not just slightly stronger than a magnitude 8, it is dozens of times more powerful. When this logic is applied to the great events of the Ring of Fire, the difference becomes almost hard to comprehend. The 1960 Valdivia earthquake, for example, is not the largest ever recorded simply because it reached magnitude 9.5. It is the largest because it released such an immense amount of energy that it surpasses, on its own, the combined energy of thousands of smaller earthquakes. Compared to a magnitude 7 tremor, it released energy equivalent to tens of thousands of such events combined. This understanding completely changes how we look at seismic rankings. It is not just about ordering numbers, but about recognizing massive jumps in energy. A magnitude 8.8 earthquake, like the Kamchatka event, is already extreme on a planetary scale. Yet it still releases less than half the energy of a magnitude 9.5 earthquake. This invisible difference is crucial for explaining why some earthquakes generate global tsunamis while others remain more localized. Another fundamental aspect in comparing the largest earthquakes in history is the distinction between magnitude and intensity. Magnitude is a physical measure of the energy released at the earthquake source. Intensity, on the other hand, describes the effects observed at a specific location, how strongly the ground shook, the damage to buildings, and the impact on people. The same earthquake can have very different intensities depending on distance from the epicenter, focal depth, and local soil conditions. This distinction explains why some extremely powerful earthquakes cause less direct destruction than smaller ones. A deep megathrust earthquake occurring far from densely populated areas can release colossal energy without causing the same level of urban devastation as a shallower quake closer to a major city. From a geological perspective, however, it remains far more significant. When comparing the largest earthquakes of the Ring of Fire, scientists also analyze rupture duration. Typical earthquakes last seconds. The largest last minutes. This difference is critical. During a megathrust event, the fault ruptures progressively, like a gigantic zipper opening beneath the Earth's crust. The larger the ruptured area and the longer this process lasts, the greater the energy transferred into the planet and the oceans. These details are obtained from global seismic networks spread across every continent. Today, a major earthquake is recorded simultaneously by hundreds of stations worldwide. This allows scientists to reconstruct the event in remarkable detail, from the initial rupture point to how the energy propagated through the Earth, traveling through the mantle and being detected on the opposite side of the planet. Comparing historical earthquakes from before the 20th century is even more challenging. For older events, scientists rely on historical records, written accounts, sediment layers left by tsunamis, and geological deformations preserved in the landscape. From this indirect evidence, models are built to estimate probable magnitudes. Even with uncertainties, many of these events reveal that the Earth has produced earthquakes comparable to the largest ones recorded instrumentally. In the context of the Ring of Fire, these comparisons reveal an unsettling pattern. The largest earthquakes on Earth are not randomly distributed. They are concentrated almost exclusively in oceanic subduction zones, where enormous plates collide and accumulate tension over centuries. It is there that the crust stores enough energy to produce events with magnitudes greater than 9. This realization has profound implications for both the present and the future. When scientists compare magnitudes, they are not just looking at the past. They are trying to identify regions that have not yet released all their accumulated energy. Areas that have not experienced major earthquakes for a long time may, paradoxically, be the most dangerous, precisely because stress continues to build silently. The Kamchatka earthquake reignited this debate. Although it was not the largest in history, its high magnitude combined with the region's tectonic context led experts to reassess seismic models and risk scenarios. Compared to the giants of the past, it showed that the region remains active and fully capable of producing even larger events in the future. In the end, comparing the largest earthquakes in history is not an exercise in scientific curiosity. It is an attempt to understand the limits of the Earth itself. Each number represents a moment when unimaginable forces were released, reshaping landscapes, oceans, and human societies. The magnitude scale is the language we use to translate this power, an imperfect but essential language that reminds us we live on a planet that is never truly at rest. And the more we learn to compare these events, the clearer one unsettling fact becomes: the largest earthquakes ever recorded are not rare anomalies. They are part of the normal functioning of the Earth. The Ring of Fire simply shows us, more explicitly, just how dynamic and powerful the world beneath our feet truly is. For a long time, major earthquakes were treated as inevitable tragedies, forces of nature as powerful as they were incomprehensible. The earth shook, cities were destroyed, and after the initial shock, only unanswered questions remained. But every megathrust earthquake that occurred in the Ring of Fire left behind more than ruins, it left data. And that data, analyzed over decades, profoundly transformed what science understands about how the planet works. The first major lesson came from the realization that the largest earthquakes do not occur randomly. They follow clear geological patterns, linked to the dynamics of tectonic plates. Before the 20th century, many scientists believed earthquakes were isolated events, with no connection to one another. Today, we know they are part of long cycles of energy accumulation and release, especially in the subduction zones that dominate the Ring of Fire. The 1960 Valdivia earthquake was a turning point in this understanding. For the first time, instruments spread across the globe recorded a seismic event so powerful that its waves traveled around the planet multiple times. This allowed scientists to observe how seismic energy propagates through the Earth's interior, revealing previously invisible details about the mantle and the core. The Earth was literally used as a natural laboratory. From this event onward, it became clear that the Earth's crust does not rupture all at once. In megathrust earthquakes, the rupture propagates along the fault for hundreds, sometimes thousands, of kilometers. This process can last several minutes, releasing energy progressively. This discovery completely changed seismic models, which had previously assumed much simpler and more localized ruptures. Another fundamental lesson was understanding the role of friction between tectonic plates. In subduction zones, plates do not slide smoothly. They become locked, accumulating tension for decades or centuries. When this tension exceeds the strength of the rocks, a sudden release of energy occurs, what we call an earthquake. The megathrust earthquakes of the Ring of Fire showed that this locking can occur over enormous areas, creating events on a continental scale. The 1964 Alaska earthquake reinforced this idea. It revealed that not just a single fault was involved, but an entire system of interconnected faults. The crust does not behave like a straight line that snaps, but like a complex network of blocks that adjust violently against one another. This understanding led to the development of three-dimensional fault models, something essential for modern seismic monitoring. With the 2004 Sumatra earthquake, science learned an even harsher lesson: earthquakes do not end when the ground stops shaking. The rupture of the ocean floor displaced billions of tons of water, generating a tsunami that crossed oceans and struck countries far from the epicenter. This event showed that the true impact of a megathrust earthquake can extend for hours or days, affecting entire regions of the planet. After this tragedy, there was an unprecedented advance in tsunami warning systems. Networks of underwater sensors, pressure buoys, and satellites began to be integrated in real time. Science learned that seconds and minutes save thousands of lives. Although it is still not possible to predict an earthquake, it has become possible to respond much faster to its secondary effects. The 2011 Tohoku earthquake in Japan brought even deeper, and more uncomfortable, lessons. Japan was considered one of the most prepared countries in the world for earthquakes. Even so, the magnitude of the event exceeded many predicted scenarios. This forced the scientific community to acknowledge that risk models had been underestimating extreme events. After Tohoku, it became clear that some subduction zones are capable of producing earthquakes much larger than previously imagined. Segments once considered moderate revealed the potential for gigantic ruptures. This recognition led to global revisions of seismic risk maps, especially along the Ring of Fire. Another crucial lesson involved cascading earthquakes. In megathrust events, the release of energy in one region can alter the stress field in neighboring areas, increasing the likelihood of new events. This does not mean one earthquake directly causes another, but that it can act as a trigger in already stressed systems. This idea changed how scientists interpret seismic sequences. The study of major earthquakes also revealed that the Earth responds slowly to these events. After a megathrust earthquake, the ground can continue deforming for years, in a process known as post-seismic deformation. High-precision satellites have shown that entire continents can shift by several centimeters after a single event. The planet, even after the rupture, is still readjusting. In recent years, science has begun integrating seismic data with satellite observations, artificial intelligence, and advanced computational modeling. This has made it possible to identify subtle patterns that were previously invisible, such as small ground deformations and microtremors that precede major events. While this still does not allow exact predictions, it significantly improves risk assessment capabilities. The recent Kamchatka earthquake reinforced many of these lessons. It showed that less monitored regions can still surprise scientists with high-magnitude events. It also highlighted the importance of integrated global seismic networks capable of rapidly detecting changes in tectonic behavior in remote areas. Perhaps the most important lesson of all is this: the absence of large earthquakes does not mean safety. Many of the most dangerous zones in the Ring of Fire are precisely those that have been silent for decades or centuries. Science has learned that seismic silence can be a sign of accumulated energy, not stability. Today, past megathrust earthquakes are used as reference scenarios for future simulations. They help answer fundamental questions: how far can the Earth go? What is the limit of the energy that can be released in a single rupture? And, most importantly, how can humanity adapt to a planet that is in constant motion? The Ring of Fire has made it clear that we do not live on a static surface, but on a dynamic, powerful, and unpredictable system. Every major earthquake teaches something new, not only about geology, but about vulnerability, preparedness, and respect for natural forces. By studying these extreme events, science does not seek to control the Earth, something impossible, but to understand its signals, reduce risks, and save lives. And paradoxically, the more we learn, the clearer an unsettling truth becomes: the largest earthquakes on the planet are still part of our future. They are not exceptions of the past. They are recurring chapters in Earth's history. In some moments, it only appears silent. And it is precisely this silence that most unsettles scientists. When we analyze recent seismic events around the Pacific, what emerges is not a story of constant chaos, but a far more subtle, and therefore more dangerous, pattern. Small tremors, almost imperceptible adjustments, sequences of moderate earthquakes, and prolonged intervals without major ruptures form a complex mosaic that reveals the planet's current state of tension. In recent years, seismic activity in the Pacific has shown behavior characteristic of regions accumulating energy. Instead of frequent, isolated major earthquakes, what is observed is a multiplication of intermediate events spread along tectonic plate boundaries. These tremors rarely make global headlines, but they are carefully monitored because they act as internal adjustment signals within the Earth's crust. Modern science understands that the absence of megathrust earthquakes does not mean relief. On the contrary, regions that go long periods without releasing large amounts of seismic energy may be entering a critical phase of the tectonic cycle. It is like a spring being slowly compressed. The longer it remains under pressure, the greater the potential energy stored. In the Pacific, this behavior is observed in several subduction zones. Some have already produced giant earthquakes in the past and have remained relatively quiet ever since. Others have not yet released all the energy accumulated since the last major recorded event. When scientists analyze these patterns, the question shifts from if a major earthquake will occur to when and where. Recent events show that the Pacific is going through a phase of stress redistribution. Small and medium earthquakes act as partial release valves, but they rarely relieve pressure in a significant way. In many cases, they simply transfer stress to adjacent fault segments, increasing risk in neighboring areas. This explains why moderate earthquakes can precede much larger events. Another crucial factor revealed by current events is earthquake depth. Deep earthquakes indicate processes occurring within the subducting plate, while shallow earthquakes are more directly associated with plate boundaries, the most dangerous type for the surface. Recent monitoring shows an unsettling combination: continuous deep activity accompanied by sporadic shallow events, a typical pattern of tectonically loaded regions. Technological advances have made it possible to observe these signals with unprecedented precision. Satellites detect millimetric ground deformations. Seismic networks capture microtremors that would once have gone unnoticed. Algorithms analyze massive volumes of data in search of patterns the human eye cannot detect. Even so, the conclusion remains uncomfortable: seismic risk in the Pacific remains high. Recent events have also reinforced the importance of earthquakes that are felt but not destructive. In many Ring of Fire regions, populations have reported light to moderate shaking, enough to cause alarm, but not significant damage. These events have an important psychological impact, constantly reminding people that the ground beneath their feet is moving. For science, they are essential pieces of a much larger puzzle. Another aspect revealed by recent activity is the global interconnectedness of tectonic systems. A major earthquake in one part of the Pacific can alter stress fields in distant regions, temporarily increasing or decreasing the likelihood of new events. This dynamic shows that the Ring of Fire is not a collection of isolated zones, but an integrated system that responds as a whole. Current data also indicate that some highly populated urban areas remain exposed to significant risks. Many of these cities grew rapidly throughout the 20th century, often without considering the long-term behavior of geological faults. Today, millions of people live on or near zones capable of producing large-magnitude earthquakes. Recent events serve as silent reminders of this vulnerability. From a scientific perspective, one of the most closely observed signals today is so-called anomalous seismic silence. In certain regions, activity has decreased more than expected based on historical patterns. Far from being reassuring, this phenomenon may indicate that plates are strongly locked, accumulating energy over long periods. It was precisely this type of behavior that preceded some of the largest earthquakes of the past. At the same time, other areas exhibit the opposite effect: prolonged sequences of moderate earthquakes known as seismic swarms. These events lack a clear main shock, but show that the system is in constant readjustment. While they rarely evolve into megathrust earthquakes, they indicate that the Earth's interior is active and unstable. Recent events also highlight an important limit of human knowledge. Despite all available technology, science still cannot accurately predict when and where a major earthquake will occur. What it can do is identify higher-risk regions, monitor subtle changes, and improve response capabilities when the inevitable happens. This uncertainty may be the most powerful message left by current Pacific seismic activity. We live in an era of abundant data, advanced models, and constant surveillance, yet we still depend on the Earth itself to reveal its next moves. Every small tremor is an incomplete sentence in a language we are still learning to decipher. Recent events show that the Ring of Fire remains true to its reputation, a region of accumulated energy, ready to release forces capable of reshaping landscapes and societies. There are no signs that this activity is permanently decreasing. On the contrary, all indications are that the Pacific tectonic system remains active, dynamic, and potentially dangerous. When observing the present, science does not see a calmer planet than in the past. It sees a planet in constant adjustment, following cycles that have repeated for millions of years. Current seismic risk is neither greater nor lesser because of humanity, it is simply part of Earth's nature. What has changed is the number of people, cities, and infrastructures exposed to that risk. In the end, recent events do not bring a message of panic, but of awareness. They remind us that living around the Pacific means coexisting with deep and inevitable forces. The question is not how to prevent major earthquakes, but how to better understand their signals, reduce vulnerabilities, and respect the limits of a planet that is always in motion. And the more we observe what is happening today, the clearer it becomes that the past of the Ring of Fire is not behind us. It continues to be written, tremor by tremor, beneath oceans and continents, silent, patient, and powerful. The largest earthquake ever recorded in the Ring of Fire is not just an event from the past. It is a silent warning, engraved in the geological memory of the Earth, about what the planet is capable of doing, and will continue to do. When the crust ruptured with a force never measured before, it was not a rare accident or an isolated anomaly. It was the extreme manifestation of a process that happens continuously, far beneath our feet. The main lesson left by this event is simple and unsettling: the Earth is not in static equilibrium. It is in constant transformation. Tectonic plates move just a few centimeters per year, almost imperceptibly, but over decades and centuries this movement accumulates enough energy to redefine entire landscapes in a matter of minutes. The largest earthquake in the Ring of Fire showed that the planet does not need millions of years to change. Sometimes, it needs only a few moments. This event also revealed that the limits of terrestrial force are far higher than humanity once imagined. Before it, it was believed that there was a natural ceiling for earthquake magnitude. That ceiling was broken. The Earth showed that it can release energy on scales that surpass any human reference. Since then, science has begun to look at subduction zones with a new level of respect and caution. The future of the planet, from a tectonic perspective, will not be marked by stability. On the contrary, as plates continue their inexorable movement, new tensions arise while old ones are redistributed. The Ring of Fire will continue to be the stage for the greatest adjustments of the Earth's crust, simply because it brings together the ideal conditions for this: gigantic plates, deep oceans, and long, complex subduction zones. Another fundamental lesson is that major earthquakes do not clearly announce their arrival. The largest event in the Ring of Fire was not accompanied by obvious signals that could be interpreted as a definitive warning. There were small tremors, local adjustments, subtle signs, but nothing that allowed for precise prediction. This makes it clear that even in the future, humanity will continue to live with a significant level of uncertainty. This uncertainty reshapes our relationship with the planet. The future will not be only about predicting events, but about learning to coexist with them. Cities will need to be designed based on extreme scenarios, not just historical averages. Critical infrastructure will have to consider the possibility of rare but devastating events. The largest earthquake in the Ring of Fire showed that the improbable is not impossible. The impact of this event also revealed something profound about the planet's interconnectedness. An earthquake occurring in a specific band of the Pacific was able to generate effects felt on distant continents, alter sea levels, modify wave patterns, and even influence measurements of the Earth's axis. The future of the Earth will increasingly be understood as an integrated system, where local events can have global consequences. There is also an unavoidable human lesson. The largest earthquake in the Ring of Fire exposed the vulnerability of modern societies to natural forces. Technology, engineering, and planning reduce risks, but they do not eliminate the possibility of severe impact. The future will require not only technical solutions, but a cultural shift in how we perceive natural risk. At the same time, this event revealed humanity's capacity to learn. Every major earthquake generates scientific advances, improvements in warning systems, new construction models, and more efficient response strategies. The future will not be just a repetition of past tragedies, but a continuous process of adaptation. The Earth will continue to move, the question is how prepared we will be when it does. The largest earthquake in the Ring of Fire also reminds us that geological time and human time operate on different scales. What seems rare to us is recurrent for the planet. A mega-earthquake every few centuries is not an exceptional event from the Earth's point of view. It is part of a natural cycle that will continue long after our generation. Looking ahead, science knows that other major earthquakes will come. Some may approach the magnitude of the largest ever recorded. Others may surpass it. Not because the Earth is becoming more unstable, but because it is simply following its natural course. The Ring of Fire will continue to be a frontier between colossal forces, where the crust is constantly tested to its limit. In the end, the largest earthquake in the Ring of Fire is not just a story about destruction. It is a story about planetary humility. It reminds us that we live on a thin surface, floating above forces we do not control. But it also shows us that understanding these forces is the first step toward coexisting with them. The future of the planet will not be defined by the absence of earthquakes, but by our ability to understand the dynamic world we live in. The Ring of Fire will remain active, silent, and powerful. And every tremor, large or small, will be another reminder that the Earth is alive. And perhaps that is the greatest revelation of all, the largest earthquake in the Ring of Fire was not an outlier. It was a reminder. A warning that we live on a living, powerful, and unpredictable planet. And that no matter how much we advance in technology and knowledge, we are still temporary guests on a surface in constant transformation. Every major earthquake leaves marks not only on the ground, but on the memory of humanity. They force us to look downward, into the earth, and also inward, questioning how much we truly understand the world we call home. If you've made it this far, it's because you also feel this restless curiosity about the mysteries that shape the planet. So keep exploring. Subscribe to the channel, leave your comment, and share this video with those who believe that the Earth still holds secrets far greater than we imagine. Because while the world seems solid, the real mystery lies beneath our feet.